Chapter 9, and estimation and confidence intervals, okay? And so it's going to take into consideration what we did last week in regards to the central limit theorem. And so after tonight's class, what you'll be able to do is you'll be able to make estimates of population means, or population proportions, or population percentages. So after today, you'll be a statistician. You can go out and make an estimate as to what you predict will happen, or what the population mean is. And so if we just turn to page 298 for a moment, it says 9.2, point estimate for the population mean. So the sample mean is a point estimate for the population mean. However, the sample mean is rarely the population mean. And so if it's rarely the population mean, the sample mean, then it's better to take that sample mean and expand it out into an interval. And when you make your estimate for the population mean based on the sample mean, it's what we call a confidence interval. And so it will be something like sample mean. Let's say the sample mean is 10. We're going to do a calculation that will say the confidence interval is 10 plus or minus 3. And there's a calculation that will derive the 3 based on the central limit theorem. So really, if the sample mean is 10, and you expand it out into an interval by plus or minus 3, then your interval estimate will be 10 minus 3, which is 7, through 10 plus 3, which is 13. So your estimate will be the population mean is somewhere between 7 and 13. And that's what we say when we make our confidence interval estimates in statistics. And so that's what we're going to do in this chapter right here. 299, confidence interval, just reading. It says a range of values constructed from sample data so that the population parameter is likely to occur within that range at a specified probability. And so the specified probability is what we call the level of confidence. So when you say that the population mean is somewhere between 7 and 13, you're also going to say something to the effect that, well, with 95% confidence, or with 99% confidence. And if you say 95% confidence, that means that one time out of 20, which is 5 divided by 100, you're going to be wrong when you make your estimate. If you have 99% confidence, probability says that you're going to be wrong 1 out of 100 times. And you get to choose the level of confidence. Okay. So I have a handout here that we're going to use. It's 4 pages. I think it's 4, maybe it's 5. So I will hand it out right here. And we're going to go over that, or this. When you're asked the question about statistics, you say confidence interval. Let me get out this little handout here, because with this handout,
will we be allowed to use this on the test?
Yes, you are. Everything's its own book, so you can use it on the homework. You can use it on the final exam. You can use it in your workplace. Okay, so. What it has right here is if I look at it, this is a figure 1, which is a decision tree, and we'll read that in a minute. But before we get there, just let's look at the 4 pages of this handout. And okay, the first 2 pages, I believe, it says the confidence interval formulas for estimating mu. Is that what it says? The first page. Okay, and then the 3rd page says confidence interval formulas for estimating pi, right? Those are the pages 3 and 4. Everybody see that? Yep. Okay, so the first two pages are for when asked, estimate mu using confidence intervals. And then the last two pages are for using confidence intervals for estimating pi. What's pi? Population proportion. What's mu? The population mean. And everything is designated under where. See at the bottom of the first page where it says where, you go over to the second page, and so what do you see? No, actually no, it's at the bottom of this first. All right, I got these mixed up here myself, so. Okay, so on the first page, it ends up where, and then on the second page, there's the definition of all the different symbols, where it says mu is the population mean. Everybody see that? Okay, and then on page 3, this is confidence intervals for estimating pi, and so if you go to the second page, pi is the population proportion. Everybody see that? Mm-hmm. Okay. All right, so if one were to estimate mu using a confidence interval, what one would do is one would look at the first two pages of this handout. And if you look at the first page of this handout, it's broken into two different sections. One says for large populations, and the other one says for small populations. And so the first thing you do when you construct your confidence interval is you say, do I have a large population or a small population? And so if you were to compare the first formula under the large population and compare it to the first formula under the small population, what are the differences in those formulas? And the only difference is that for small populations, there's this calculation called FPC. That's the only difference between the formulas. And FPC stands for what? Go over to the next page. FPC stands for the finite population correction factor. And so I forgot to write this down, but write this down on the handout. FPC, finite population correction factor, is equal to the square root of the population size minus the sample size divided by the population size minus 1. Okay, so when one uses the finite population correction factor, what do you have to know in order to calculate it? You have to know large n. What's large n? Population size. You have to know small n. What's small n? Sample size, but you're taking a sample, so you definitely know that. What's big N again? Population size? All right, and so therefore, in order to calculate the FPC, you have to know the population size. And so that's the giveaway in a question that I or the textbook might ask you. They might say, here's some data. And if they give you the population size, or if I give you the population size, I am forcing you to this formula with the FPC. Okay? So make sure that you use the formula for small populations when I or the textbook give you the population size. Okay? All right. So that's one of the differences in the four formulas that are on this first page. The second one is, if you compare the first formula for large populations to the second formula for large populations, what are the differences? Well, the differences are, they both start out with X bar. What's X bar stand for? Sample mean. So you have to know the sample mean, but you're going to know that because you're taking a sample. You're going to calculate the mean. And then it says minus z sub alpha over 2 times sigma divided by the square root of n. For the second formula, it says instead of z alpha over 2, it says t sub alpha over 2, comma n minus 1 times s divided by the square root of n. And so one of the differences in this formula is that for the first one, you have to know sigma. What's sigma?
Standard deviation.
Which standard deviation? No,
Population.
remember,
Population.
everything's under where. If you look over where, it says sigma is the population standard deviation. Okay? Versus S. What's S?
Sample
S is the sample standard deviation. And then there's a Z versus a T. And so when do you use a Z versus a T? And so that is the decision tree. So I gave you another handout, okay, where it has a decision tree. And so what happens is that you use this decision tree to determine if you have a Z distribution or a T distribution. And when you have a Z distribution, you use the formula with the Z sub alpha over 2. If you end up with the T distribution, you use the formula with the T sub alpha over 2. Okay? So when do you have a Z versus a T distribution? And so the first question that you ask yourself is the population normal? And most of the time, we don't know anything about the population. And so most of the time, the answer is, I don't know. And so that basically is a no. And so what you do is you go to the left. And the next question is N 30 or more? And so what's N? Little n is the sample size. And what happens if n is 30 or more? You can rely on the central limit theorem. And so it says, is n 30 or more? But then there's an and. And is sigma known. And so if n is 30 or more and sigma is known, what kind of a distribution do you have? Z. And so you use the formula with the Z. If the answer to that is n 30 or more and is sigma known, and the answer is no, it says go to another chapter in the book. And so you know at this stage of the game, you should never be in the bottom left corner because we haven't gotten to that chapter yet. And we won't get to that chapter in statistics too. So if you end up in that box, sometimes you do because the book on these examples is not very good in telling you to assume a normal distribution. So if you read it and the textbook example doesn't say anything and you end up in the far left box, what you should do is you should go back and say, well, even though they didn't tell me, I'm going to assume it's normal. They'll force you over to the right on the decision tree. And then it says, is the population standard deviation known? If the answer is yes, you have a Z distribution. If the answer is no, you have a T distribution. Everybody follow how you use this right here? Okay, pretty straightforward. And so when it comes to confidence interval construction, if I say construct a confidence interval, you should take out these handouts and say, okay, I know it's going to be one of these formulas. Which formula is it? Well, did he give me the population size? And if the answer is no, and I can't use the FPC, so it has to be a large population, then is it a Z or T? This handout here tells you if it's a Z or T. Okay? And so, before we get to the T distribution, which is a new distribution, all we know at the moment is a normal, the Z distribution. The T distribution is also a normal distribution, but we're going to get to that in a minute. But before we get to that, what we're going to do is we're going to construct a confidence interval for something. And so let's say that the question is estimate average commute time to Boston. Okay, yep, sorry.
What determines the difference between a large population and a small in numbers? Is it?
What do you
The
mean?
difference between a large and a small population?
For confidence interval construction purposes, whether or not you have to use FPC. Because like I said, if you look at these two formulas, what's the difference between the first formula under large populations and the first formula under small populations? There's no difference other than the FPC, right? And the FPC is the finite population correction factor, which I just changed, which I just erased. And in order to calculate it, you have to know the population size. So if you know the population size, it's considered a small population, even if the population size is like 3 million. Okay? So estimate the average commute time to Boston. How many, I don't know if we did it last time, but let's say there's what, 2 million commuters to Boston? 2 million commuters. And so what we're gonna do is we're gonna we're gonna estimate their average time. But we don't have time and we don't have the money to survey 2 million commuters. And so what we do is we say, oh, I know how to construct a confidence interval using statistics. And so therefore, that's what I'm gonna do. I'm going to construct a confidence interval. And so, because we're looking at the z-distribution, I want to make sure you end up in the z-box. And so what I'll say is, let's assume a normal distribution. Also going to say that sigma is equal to 15 minutes. That's a given. All right, so we'll say sigma is equal to 15. Like I said, most of the time you don't know anything about the population, but in order to explain the z-distribution and the confidence interval construction, I have to give you sigma. And so in some examples you'll know sigma, in some examples you won't have it, and you'll have to standard deviation is such and such. Okay, so in this example right here, assume a normal distribution, and we'll say that we know sigma is equal to 15 minutes. And so we're also going to say that we don't have time to survey 2 million customers, we have time and money to survey 100 commuters. So we're going to sample 100 commuters, and we're going to construct a confidence interval, and we'll say that we're going to, the confidence level, how do we designate the confidence level in this formula? If you look on the second page, what does it say about the level of confidence? What's that equal to?
Z-score.
What does it say on the second page here?
Oh,
What's
1
the
minus
level of
A.
confidence? 1 minus alpha. 1 minus alpha is equal to the confidence level. And we get to pick the confidence level. And so let's pick 95%. Okay? You could pick 90, you could pick 99, but for this example, we'll pick 95%. So the basic question is, construct a confidence interval estimate for mu with 95% confidence. All right? So, I'm trying to determine which formula it is. We go to the decision tree. What's the first question? Is the population normal?
Yes.
And the answer is yes. You go to the right. Is sigma known?
Yes.
Yes.
And so what do you have?
Z.
Z-distribution. And so then it comes down to, okay, is it a large population or a small population? What's the difference between the two? In order to do the small population, you have to know the population size. And so do we know the population size?
Yes.
Yeah, okay, well, I didn't want to do it with knowing the size, but that's okay, we'll deal with it. We'll deal with the population size, an additional calculation that I didn't want to have to make the first time, but we'll deal with it. And so we say that, okay, n is 2 million. And so, so it's the first formula under the small populations, correct?
Yes.
Right, and so let's just write it up on the board. What does it say? It says probability of X bar. Oh, we didn't even take our sample yet. I forgot, we gotta go take a sample. So let's say we go take a sample, and X bar is equal to 87 minutes. What's X bar?
Sample mean.
Sample mean. How do you get a sample mean from 100 observations? You total up all 100 numbers, you divide by 100, and we got 87 minutes. Because it's an average, it's the sample average, sample mean, sample average. So, the formula says X bar, so what we're gonna do is, right there, we're gonna put the sample mean in, and then it says, I'm just gonna write stuff up here, Z alpha over 2, and it's a subscript, times sigma divided by the square root of n, And then it's the finite population correction factor. And it says less than or equal to mu, less than or equal to, and I'm gonna have to go on the other board over here. It says x bar plus z alpha over 2 sigma divided by the square root of n, big N minus little n, big N minus 1 is equal to 1 minus alpha. Oh, and what's alpha?
Nothing but.
0.95, right? So we can plug that in here. We can plug a 0.95 in here. Well, actually, no, we'll put that in a second. This is just 1 minus alpha. So now what we're going to do is we're going to plug in the different variables that we have here. And so what's x bar? X bar is 87. So it's 87 minus z alpha over 2. We'll get to that in a minute. Sigma. What's sigma?
15.
15 minutes. Divided by the square root of 100. Times. What's big N?
2 million,
2 million.
2 million minus what?
100.
Over 2 million minus 1. Less than or equal to mu. Less than or equal to the same thing on the other side, except we're going to add. So it's going to be 87 plus z, we'll get to that in a minute, 15 divided by the square root of 100 times 2 million minus 100 divided by 2 million
Minus 1.
minus 1 is equal to 0.95. Okay, so we have to find z. Z's pretty easy. Does it say anything on the handout? What's it say on the handout?
It's either one.
It says z is the appropriate z-score for the given level of confidence. It's either 1.96 or 2.57, most of the time. And so, what do we have here for the level of confidence? 95%.
0.95.
Okay? How does that relate to z? Well, if you go to the table, and because, remember, the central limit theorem looks something like this. This is a minus z and a plus z. What's the area under the curve between minus 1.96 and plus 1.96 on a z basis? If you go look up 1.96 on the z table, what do you get? You get 0.4750. Correct? And minus 1.96 is 0.4750. So what is 0.4750 plus 0.4750?
0.95.
0.95. And so when you have 95% confidence, the central limit theorem says something to this effect about the sample means. And so therefore, z with 95% confidence is always going to be 1.96. Always 1.96. And so all we do here is we put in a 1.96, we put in a 1.96. I'm going to be multiplying it. Now, if you look at 2.57 on a z basis, minus 2.57 plus 2.57, and you look up z, what does it have as the area under the curve between z equals 0 and z equals 2.57? If you look up 2.57, what do you see? 2.57 is 0.4949. And what's 0.4949 plus 0.4949?
0.99.
0.99, meaning 99% of the sample means are between minus 2.57 and plus 2.57. So if you have 99% confidence, Z is always going to be 2.57. And in statistics, we tend to use just those two, 99%, 95. Every now and then we do 90, but you can choose anything you want, really, 88, anything. But most of the time, it's 99 or 95. So when you're doing confidence interval construction, if you have a Z distribution and you have 95% confidence, then Z is always going to be 1.96. Everybody understand? Okay. And so if you just solve for this right here, it's 87 minus this. So what is it? It's 1.96. 15 divided by 10. What's 15 divided by 10? 1.5. Oops. Times this thing, the finite population correction factor. I'm sure somebody's got a calculator about. What's 2 million minus 100 divided by 1,999,999?
It's 0.9 repeating.
Right, so it's 0.9999. Let's just say it's 4 nines. Less than or equal to mu, less than or equal to 87 minus, plus 1.96 times 1.5 times 0.9999 is equal to 0.95. And so, bad board management here, but we have probability 87 minus what? Well, what's 1.96 times 1.5 times 0.9999? What do we get for that?
2.9396.
2.93, less than or equal to mu, less than or equal to 87 plus 2.93 is equal to 0.95. And so if we go up over here, so we have what? Probability, what's 87 minus 2.93? 85, 84, 87, 85, 84, is it 8407? 5, yeah, 8407, right? Is that right?
Yep.
And what is it? It's minutes. Less than or equal to mu, less than or equal to 87 plus 2.93 minutes, so it's 89.93 minutes. Is equal to 0.95. And so that is our estimate for the average commute time of the 2 million workers that commute to Boston. It's what? It's that. What does that say? That says we are 95% confident that mu, the average commute time of workers to Boston is between 84.07 minutes and 89.93 minutes. Now, 07 is in hundredths, so I don't know, what's that? Probably 2 seconds or something, so it's 84 minutes, 2 seconds. Or whatever 0.07 minutes is, I don't know, but that's our 95% confidence interval estimate for the average commute time of workers to Boston is between 8407 and 8993 minutes. And that's all you have to do. You take a sample of 100, find out what kind of a distribution you have, plug it into the formula, calculate it, and you get your estimate. And so when you look at this estimate right here, what does it do? It takes into consideration all the information you know. And the information you know is that It has a population size of 2 million, so we factored that in. It has a sample mean of 87. That's a statistic. We put that in here. We also know, for some reason, that the sigma was 15 minutes. We put that in here. And the 1.96 comes from the central limit theorem. And as does sigma divided by the square root of n, because that was the standard error in the central limit theorem that we put up last week. And so it takes into consideration the standard distribution, the central limit theorem, the population size, the sample mean, and the population standard deviation. So it made use of all the information, and statistically it came out to have an average of between 8407 and 8993, which is 87 plus or minus 2.93 minutes. Okay, pretty straightforward confidence interval construction. And so let's say that we did not know the population size. And so what would be the only thing that would change? The only thing that would change is what? We don't have to do the FBC. Okay, so if you crossed out FBC in this case, how would the answer change? It wouldn't change at all. Why? Because 87, 1.96 times 1.96 times 1.5 is probably still 2.93. And so basically, even though we made use of the FBC, it didn't really mean anything in the context of this estimate. But if you do know the population size, you should use it, because using information is what makes statistics better. Always use all the information that you have. Okay? Anybody got any questions on confidence interval construction using Z for the mean?
I have a question. If we didn't use the FPC, that would mean that the population, it would be considered a large population?
Yes, you would use the formula for large populations.
Okay.
And so, in this case, it wouldn't have mattered if you used it or not, because 0.9999 doesn't influence 2.93. But as I said, what will happen is if I give it as a question, I'm not going to say the population size is 2 million. I might say the population size is like, 2,000. Because what would happen if the population size were only 2,000? It would be, what's 2,000 minus 100? Divided by 1,999, and you took the square root of that, right?
Correct.
Yeah, okay, so do that calculation. Let's say it's 2,000 minus n divided by 1,999, and take the square root of that. What do you get for that?
0.97.
0.97 times 1.95 times 1.96.
1.96 is 2.9.
2.9. So what would it would be 87 minus 2.9, 87 plus 2.9, correct? What would this look like over here then? This would be 84, what is it, 2.9? 84.1 and 89.9, correct? Is that a wider interval or a tighter interval? It's a tighter interval, right? Because it's not 87 plus or minus 2.93, it's 87 plus or minus 2.9. So the interval's tighter. Tighter intervals are better. In this case, not much better, but in statistics, we want to make the best estimate. We want to make the tightest interval estimate we can. And basically what this saying is here, it says, look at, we only surveyed 100 out of 2 million. That's not many. So we don't get much of a credit from a finite population correction factor because we didn't survey much of the population. But when it's 2,000 versus 100, that's a much better selection on a relative basis. And so therefore, we get credit for serving, or for sampling more of the population on a relative basis, meaning that the interval gets tighter, and that's better. Also saying, and once again, that we said last week, The bigger the sample size, the better the estimate. Why? Because it's a tighter estimate. Okay, because what would happen if the sample size went up from 100 to 1,000? This is in the denominator. It makes this number less. A smaller number times a number gives you a smaller number. And so the 2.93 would be smaller. And so it would be 87 minus 2 point, something less than 2.93. 87 plus something smaller than 2.93. Tighter intervals. Tighter intervals are better. Why? You surveyed more. You sampled more. You get credit for that in statistics. Everybody understand that? Okay? So the object of the game is to get as big a sample as you can, but that's also a function of time and money. How much money is available, how much time is available, that dictates your sample size. Okay, I can erase this? Everybody's fine with this? Okay.